Hey everybody. The purpose of today's video is to talk about using the method of initial rates to determine the differential rate law for a particular reaction. Now remember that the differential rate law contains the reaction order, and that those reaction orders can only be determined from experimental data. The method of initial rates is by far the most popular method for making a decision about the orders of each reactant and the overall reaction. We're going to look at a reaction and see data where several different experiments with different initial concentrations of reactants were run. We're going to compare them and their initial rates to get the reaction order. From this, we can also determine the rate constant for the overall reaction. The more challenging part of that, perhaps, will be assigning units, which we'll also discuss very briefly at the end of this video. So let's look at a problem. Here, we have A plus B going to products, and we have run 3 individual trials of this reaction. In trial 1, both A and B were 0.1 molar. In trial 2, A was 0.2 molar and B was 0.1 molar. And in trial 3, both A and B were 0.2 molar. You can see the measured initial rate of reaction for each of the 3 trials in the table. And you'll note that that rate of reaction steadily increases as we go from trial 1 to trial 3. Let's try now to use this data to find the order with respect to each reactant, the overall order of the reaction, and the value of the rate constant. So we see our data again here. The first step in the process is to write the generic rate law. In this case, rate equals K, A to the X, B to the Y. Now we have to decide whether we want to solve for X or Y first. With the data we have here, it really doesn't matter, but we'll go ahead and solve for X first. To solve for X, we're going to look at the chart and we're going to pick 2 trials where where A and only A have changed. Those 2 trials are trial 2 and trial 1. In trial 2, A increased, B stayed the same as it was in trial 1. Because the rate of trial 2 is bigger than the rate of trial 1, and because we like whole numbers instead of fractions whenever possible, we're going to put rate 2 over rate 1. And you'll notice in the expression we've written here, we've brought along their associated rate law. Now that we have these rate laws, we can plug in the data for trial 1 and trial 2. If you survey the data here, you'll notice there's K in both rate 1 and rate 2, and that the concentration of B is the same in both trial 2 and trial 1. So both of those values will cancel out or be equivalent to 1. This leaves behind the rates. And if you take 0.302 and divide it by 0.150, you get 2.01. And if you take 0.2 and divide it by 0.1, you get 2. So we ultimately end up with 2.01 equals 2 to the x. The only possible value for x in this expression is 1. 2 to the first power equals 2. In other words, the rate equals K, A to the first, B to the Y. This reaction is first order with respect to A. Any change made to A, we expect to see a similar equivalent change in the rate. Let's go now and find Y. To find Y, we need to pick 2 reactions where B changes, but A is constant. Looking at the table, this happens in reaction or trial number 3 and trial number 2. So we plug in that data. Again, we're going to put rate 3 on top over rate 2, and that's just so that we work with whole numbers as opposed to fractions. Again, we plug in the data, and we notice there's still a k, which will be the same value in each trial, so it will cancel out. And this time, we note that the concentration of A is the same. 0.2 to the 1 over 0.2 to the 1 is 1. So both of those values will cancel out or be equivalent to 1. Now, we take 0.427 divided by 0.302. And when we do, we get 1.414 equals 2 to the y, because 0.2 divided by 0.1 is again 2. This one is not as easy to solve as it was when we solved for x. We probably could do this by trial and error, but that takes a lot of time. Instead, let's use logarithms to help us out. If we take the log of both sides, then the y exponent on the right will actually come out in front of the log. So we have log of 1.414 equals y times log of 2. We can divide log of 1.414 by log of 2 in our calculator, and if we do, we will get for y 0.5 or 1/2. In other words, the reaction is first order with respect to A and half order with respect to B. Now that we have the complete rate law, we can solve for K. To solve for K, all we have to do is pick any one trial, plug in the known value of A, B, and the initial rate, and solve algebraically for K. In this example, I have picked the data from trial 1. So we get 0.15 molarity per second equals K, 0.2 to the first power, 0.1 to the first power times 0.1 to the 1/2 power, which is 0.15 equals K times 0.0316 molarity to the 1.5 power. Solving, we get K equals to 4.74, and you'll note the units. Molarity to the minus 1/2, seconds to the minus 1. One of the more challenging things for students is to figure out the unit on the rate constant. Many can get the number, many also get the unit wrong. Let me give you a handy trick. In this reaction, it is true that the overall reaction order is 1.5. When you calculate a rate constant, take the overall order, subtract 1, and make the number negative. That will be the appropriate exponent to put on the molarity or concentration unit from your rate law, concentration portion of the unit. The time portion, in this case seconds, will always be to the minus 1 power. So our completed rate law is rate equals K, which is 4.74, molarity to the minus 0.5, seconds to the minus 1, times A to the first power, times B to the 1/2. I hope this explanation clarifies some of the trouble spots with using the method of initial rates. Please remember, there is no substitute for more practice when trying to learn this material. I look forward to seeing each of you in our next video.